Recording. Okay, so today we're talking about chapter 11. We're going to talk about half of it and the other half next time. So, chapter 11 is about distributed programming. In particular, a set of computers that are linked together by a network. Um, yeah, so you have multiple machines and they are connected via some sort of network, and you need to take care of that. The canonical example is the internet, of course. Um, And then we are assuming that each computer has an operating system that supports the concept of a process and provides network communication. Programming a distributed system then means to write a program that for each process such that all processes taken together implement the desired application. For the operating system, a process is a unit of concurrency. This means that if we abstract away from the fact that the application is spread over different processes, this is just a case of concurrent programming. So this is essentially going up in the abstraction stack. So instead of having processes concurrently interacting with each other in a single computer, then the computer becomes the atomic unit, and then the network is doing the communication among them to make the desired behavior be the collection of all of the computers. Uh, Very simple idea. And what would be the ideal understanding of this, the ideal solution, if we could interpret distributed programming as an instance of concurrent programming? Because then the techniques we have seen earlier in the book would still apply. And that's very true.
It's also very optimistic.
Well, uh, we have
You
the
know it's
benefit.
optimistic when the very next line is that distributed programming is complicated.
Yeah, but we have the benefit of foresight, right? So at the time, probably people didn't think of distributed programming in those terms. So the benefit of foresight is kind of like let making us biased because we kind of know like this is just an instance of that. But as history has proven, it is complicated for a variety of different reasons. Such as each a process has its own address space. Data cannot be transferred from one process to another without some translation. So these two sentences kind of seem disconnected, but they are connected in the following way. If you have to send something via the network, you have a sender and you have a receiver. In order to know from the sender who is a receiver, you need its own address space. You need to be able to say, this is the address space that I should send this data to. We're going to solve this problem later. Um,
Um,
yes.
there's actually a simpler interpretation of this, which is okay. Um, each process has its own memory, and if you want to send data from one process to another, well, you have pointers between the different structures, and those pointers need to be translated because they refer to the wrong memory region, we could say, right?
But you they have that's another aspect of this problem, right? Because if they have their own address space, 1000 on my memory is not the same 1000 in your memory. But I'm also bringing up that is your 1000 the one that matters?
Yeah. Um,
Because otherwise, we will not have to suffer from the translation problem, right? It's because I need to send something to somebody that the translation now is a step that we cannot avoid.
yeah, basically you need to be able to take a rooted directed graph of data, and I'm saying a directed graph because I'm talking about data in the abstract,
Yeah,
not
yeah.
thinking too hard about memory addresses.
Yeah, that's very
And then you
true.
have to basically replicate that same structure in a different process with its own local memory.
Yeah,
Yeah, that's the difficulty.
yeah. One moment. Okay, I'm back. Um, yes, that's a difficulty, but I'm bringing another one. Because you may ask yourself, why do you have to suffer from the translation? And I'm bringing it up that the reason that is not yet explicit at this point is that you need to send something to somebody, right? If you're sending to yourself, this wouldn't be needed. That's kind of what I'm trying to go for. The network has limited performance. Typically, the basic network operations are many orders of magnitude slower than the basic operations inside one process. So that's something you have to take care of. Some resources are localized. There are many resources that can only be used at one particular computer due to physical constraints, obviously. Localized resources are typically input and output, such as peripherals. They can be more subtle, such as a commercial application that can only be run on a particular computer because it is licensed there. The distributed system can fail partially, so you have to be resilient about that. And the distributed system is open. Independent users and computations cohabit the system. They can share the system resources and they may compete or collaborate. So you have the problems of security and naming, which is what I was referring to. And I think this comment should have been in here, right? We need a translation because we need to send something to somebody, and that's why we need to identify that somebody. So I think this comment could be also be applied to here, because we're going to figure that out with using names. Um, yes.
We're also finally going to be talking about name servers just a little bit.
Yeah. How do we manage this complexity? Let us attempt to use the principle of separation of concerns. We can divide a problem into an ideal case and a series of non-ideal extensions. Right? So the problem will fit into a generic rule as a base case, and you're going to make non-ideal, like corner case extensions to also handle the exceptions. And then it comes the network transparency approach. And then I have a question about this. In the ideal case, the network is fast, resources can be used everywhere, all computers are up and running, and all users trust one another. In this case, there is a solution to the complexity problem, network transparency. That is, we implement the language so that a program will run correctly independently of how it is partitioned across a distributed system. The language has a distributed implementation to guarantee this property. Each language entity is implemented by one or more distribution protocols, which are all carefully designed to respect the language semantics. For example, the language could provide the concept of an object. An object can be implemented as a stationary object, which means that it resides in one process and other processes can invoke it with exactly the same syntax as if it were local. The behavior will be different in the non-local case. There will be a round trip of network messages, but this difference is invisible from the programmer's point of view. When I read this the first time, I was kind of like, isn't this kind of what we are trying to pull off with Karuta? In the sense that there will be another process, potentially in another computer, in another continent, holding data there, and it will be, um, well, the claim that it is going to be invisible from the programmer's point of view is kind of debatable because there will be syntactical and language elements that will make it explicit that you're taking something from somewhere else. We are going a little bit further because our syntactical pollution to make that happen is less impactful. But
Um,
let's say that we buy this. The difference is invisible. Are we doing this? Are we attempting to do this as well in our project?
in some sense, we are, because we want to treat a domino relation as if it was a Carta relation kind of transparently. And this needs to abstract over the fact that domino is a separate process, right?
Exactly.
Which may be on an entirely different machine. Um,
Yeah.
Actually, there's another example that's a bit closer to home. Well, for me at least, not for you because you're using Wayland, but X11 is actually network transparent.
Makes sense. Um, and well, uh, no. What can I say, right? Because we're trying to pull off something that is has we have good reasons to think it is difficult to pull off. And in our case, I think we're going to have an even more seamless transition between the two things. Because in here, in OS, as we're about to see in today's session, it won't be exactly transparent in the programmer's point of view because you're going to have to like take the ticket manually for yourself. In our case, you just use a net sign and that's it. So I'm very curious to know if even now that we have this information that okay, this is actually hard, how bad or good it's gonna be in Carto.
Uh, in our case, it's actually a bit simpler because we're connecting to a database and we're making queries against a particular state, which may change as the program executes, but in principle, each query runs against one state, right? So there's no mutability going on within a single query. OS has a harder job to do because it also needs to be able to distribute mutable things, right?
Yeah, no, I'm not. I'm not saying that we are trying to do something harder than what they are pulling off because they are going. We have we have a smaller scope. We are only treating the databases. They are treating anything, resources and functions and objects and all that stuff, functors as well. So it's fine in the sense. I just think that this claim that is invisible, what comes to mind is okay. I'm gonna pick a program that works locally, and I will change a flag in the compiler, and it will be automatically distributed. And that's definitely not what they did. So I wouldn't call this invisible because a programmer will be actually typing the difference. So that's my only criticism. They did awesome. Everything is fine. I'm just saying that this should be because they will claim we're gonna do that with the network transparency approach.
I mean, if you think about it at a slightly higher level of abstraction, of course, the application programmer will see the difference because he needs to set up the distribution, right? But what about a library author?
No,
For
exactly. The library author won't be able to tell, and that's awesome. I'm just saying that that separation that you just did, the application programmer and the library programmer, that's a separation that is not written here.
that's fair.
And I would say that even though I wouldn't call it invisible, it's still awesome. Like you only have to care about the bridge. Everything else is the same. You don't have to like think differently. You don't have to change their function. You just have to change the arguments that how you're getting the arguments to call the function, and that's great. Um, it's just that it's on plain sight. Another possible distribution protocol for an object is the cached object. In this protocol, any process invoking the object will first cause the object to become local to it. So this is essentially a copy process, a copying process. From then on, all invocations from that process will be local ones. So this is the same as cached memory, right? So the caching in CPUs.
Yeah, kinda.
The point is that both stationary and cache objects have exactly the same behavior from the language point of view. Asterisk, assuming you are synchronizing those two things.
Ah, but you will be. That's kind of the point, actually.
There should be a footnote saying that. With the network
But that's the run.
transparency,
That's the runtime's problem, Lemus. It's not the problem of who is using the runtime. That's kind of the point.
yeah, but you were presenting this concept for the first time, and you were not going to elaborate on it until 11.6 because I was paying attention to know that. If they actually will mention that the cached object approach must have a synchronization step, otherwise it's useless. And I'm very surprised there's not even a footnote saying 11.8 will explore synchronization or whatever. With network transparency, programming a distributed system becomes simple. We can use all the techniques of concurrent programming we saw throughout the book. All the complexity is hidden inside the language implementation. Um, yeah. Translating to serial form is called marshalling, and translating back is called unmarshalling. The term I never heard those terms with these semantics. I heard the term serialization for this.
Then you clearly haven't been reading enough of Raymond's writing. He actually mentions this in The Art of Unix Programming, if I'm not mistaken.
I'm definitely not reading Raymond's enough, but I never like I don't see I haven't seen anybody using this terminology to refer to this process. As I mentioned before, serialization is usually the one that I see being used.
I mean, serialization is a newer term, right? So I
And
guess it makes sense.
I think I only seen marshalling in the sense of programming language development. I think I see it in the C generic video. Well, we can talk about that later. The idea of making a distributed language operation similar to a local language operation has a long history. So yeah, we should be careful about not reading everything because there's so many pages in here. We should skim a little bit. So beyond network transparency. So network transparency solves the problem in the ideal case, but there are problems because we usually don't deal with the ideal case. Network awareness. We'll show which distribution protocol we should use. Openness. All type information is part of the language entities, makes connecting independent computations relatively easy. Localized resources. We're going to use the functor for that. Failure detection is actually the same fault tolerance approach as normally you would do with exceptions, for example. Where failure detection breaks transparency, doing it in the language allows to be abstractions that hide defaults. These abstractions, if desired, could be used to regain transparency. Yeah, so then structure the chapter. Okay, so taxonomy of distributed systems. So essentially, this is the nomenclature, apparently, that people use to refer for particular topologies, maybe. I don't know how they call that, but it's how your system is organized. So the first one is shared memory multiprocessor. So this is essentially if you're working with threads. If you're working with threads in like C, you're doing that.
Yep.
Distributed memory multiprocessor. So this is playing Minecraft in LAN. Distributed memory multiprocessor with partial failure. So this is still Minecraft because if a friend fails, drops from the call in the game, you can still play the game, assuming he was not the one hosting the server. And finally, open distributed system, which is assuming that you cannot trust people, right?
Yeah, you're now on a public network instead of a private LAN.
Yeah. Um, yeah. So this is essentially explaining all of that. Yeah, there is something important here. The probability that the cluster continues to provide a service is close to 1, even if part of the cluster is failed. This property is called high availability. A cluster with the proper hardware and software combines high performance and high availability. Um, so, in the last step, the computers are connected through the internet. This adds openness, in which independent computations or computers can fight each other, connect, and collaborate meaningfully. Openness is the crucial difference between the world of high-performance computing and the world of collaborative computing. In addition to partial failure, openness introduces two new issues: naming and security. So naming is about finding one another. Well, I think this is a little bit misleading as well because this is also a problem with the LAN concept. It's not because you're introducing the internet that this becomes a problem. The introduction of the internet makes it harder to solve it, but the problem was already there from the first place. Naming is usually supported by a special part of the system called the name server. Security is how computations or computers protect themselves from each other. Yeah, so everybody knows this. So that's why you use what? HTTPS, things like that.
Yep.
The distribution model. We consider computation model with both ports and cells, combining the models of chapters 5 and 8. For communication, we can use TCP, so that's fine. Um, so yeah, 11.2 shows a computation model. So this is what we're talking about. We annotate each language entity with a process, which is the home process of that entity. It is a process that coordinates the distribution behavior of the entity. Typically, it will be the process at which the entity was first created. Um, we will sometimes use the phrase consistency protocol to describe the distribution behavior of an entity. The distribution behavior is implemented by exchanging messages between mother processes. And then it comes the hard part, because we have to support stateful, stateless, single assignment language entities. So how in the freak are going to do that? So stateless is pretty fine, right? Because they
You can just copy. That's easy.
initialization is also easy, right? Because if you have a function that is a pure function, that's stateless, you can just literally pick the verbatim implementation and use that as the serialization method, and then it's fine. But how are you going to do that with stateful entities, right?
Yeah,
Somewhere in the book,
that's much harder.
it mentions that you can also serialize the state of the mutable things at that time.
Yeah, that's not quite the same thing though, because then the state is kind of frozen at that point, right?
Yeah, you have the trade-off that you're gonna be having to like consistently updating, because we haven't reached this yet, but we're gonna write this into a file. Um, we're gonna have to keep updating this file. Like that sounds like a lot of runtime overhead. You have to pay attention
It
if
sounds like
something
a job for a
changed.
database.
Yeah, Unisom exists for a reason, folks. The distribution behavior has to be careful to maintain a globally coherent view of the state. This puts major constraints on the kinds of efficient behavior that are possible. The simplest kind of behavior is to make them stationary. What does that mean? Nobody copies anything, and everybody has a pointer that points to whoever has the ownership of that. And instead of manipulating the thing yourself, you ask that guy to do it.
Yeah, message passing. It's the Erlang approach essentially.
Yeah. An operation on a stationary entity will traverse the network from the invoking process and be performed on the entity's home process. That still sucks, right? Because if you're in China and the home process is in Brazil, that's going to take some time.
Yeah.
And then single assignment entities have one session operation, namely binding. So binding a data flow variable on binary distributed references to the same value. This operation is coordinated from the process on which the variable is created. So yeah, then there's a bunch of text. I don't know if anything here is worth reading out
Yeah,
loud.
ports are stationary while cells are not by default. Yeah, that means you can't really derive ports from cells and have distribution semantics that are nice all at the same time, which is why they are separate.
Uh, so you said that ports are stationary and cells are not, right?
Yeah, it's on this for all derived entities except for ports, they distributed blah blah blah. Yeah, that.
Mm-hmm. Therefore, distribution is asynchronous. Distributed behavior does not follow from the definition of ports in terms of cells. The ports are basic entities in the distribution model, just like cells. Um, sure. I don't see why this is not justifying to me why you're making the default for ports stationary. It's not clear to me why this justifies it, but
It's because a port is operation on a port are meant to be asynchronous, right?
sure.
Like you are already modeling message passing at the language level, so you can just use the same semantics at the distribution level, you see?
Ah, okay, so you are easing your time because you are just skipping from one level to the same semantics.
Yeah.
Cool. Uh, for example, mobile objects move to the process that is using them. These objects have the same language semantics but a different distributed behavior. Blah blah blah. Distribution of declarative data. Open distribution for global naming. Yeah, so these are essentially the approaches that you can do for naming things. An important issue in open distributed computing is the, yeah, we should read the definition of open actually. We say that distribution computation is open if a process can connect independently with other processes running a distributed computation at runtime without necessarily knowing beforehand which processes may connect, nor with the type of information it may exchange. So the internet, cool. A distributed computation is closed if it is arranged so that a single process starts, then spawns other processes on various computers it has access to. So when we were implementing Mahjong, we did that.
Yep.
An important issue is naming, as we said before. How independent computations avoid confusion when communicating with each other. So how do you know who? They do not. They do so by using globally unique names for things. Namely, instead of using print representations to name procedures, parts, or objects, we use globally unique names instead, such as references, right? So reference is an unforgeable means to access any language entity. Reference is transparent. They can be local. Can reference an entity that is localized on another process. We use this on the first version of the Erlang runtime for the logic programming thing. We dropped them later,
Uh,
but we used it.
uh, Actually, the thing that the bean calls a reference is more properly a name using the nomenclature of this book.
Really?
Yeah,
Why do you think that?
because a reference on the bean is a constant, which is unique for a particular node.
Mm.
And the only way to get that is either if you are the one who requested the node to generate it, so it's the return value of a make ref, or if you received it from somebody else. Like you can just guess a ref in the bean like that. That's exactly the same semantics of a name.
But how is that different from a reference in that case?
Uh, a reference in the nomenclature of the book is basically a data flow variable, essentially.
A data
Except it,
flow.
except you don't necessarily have the ability to make it unbound, right? So it would be more like a local variable in Erlang. Um, the thing is, you can't really share local variables in Erlang across processes, so it's not quite the same.
I'm having a hard time doing the distinction that you're trying to explain because all the properties that you listed for a reference in Erlang is also the ones that are being mentioned in here.
The difference is that in Erlang, when you do a make ref, that's an object that you can look at it and see that it is a ref type, whatever, right?
Hmm.
Um, if you look at the second phrase of the reference thingy, a reference is transparent, see? So you can't just look at it, you can only look at what it points to.
Ah. But are you but I think you can tell that it is a reference in NOS as well because you have the type information given that it's a dynamic language.
You can, but that's like, oh, actually, can you?
Well, I'm asking. My understanding is that nothing. Well, actually, they could forbid that if they just chose to not implement it. But what forbids them from implementing a function that is ref from Erlang in here? They just said
The,
themselves, right? They have type inspection.
no, but is ref in Erlang would be the same as is name or whatever in NOS.
No, it wouldn't because we're not talking about names. We're talking about a reference.
No, 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 no. You are doing the thing where you have the same concept with different names, and you are making a confusion based on the name.
I don't get it. Could you repeat that?
Like if you do make ref on the beam, okay,
Sure,
Erlang,
sure.
that returns you an atomic constant, okay, and that's just what it is. It's a constant. It doesn't really refer to anything.
Yeah.
The equivalent concept in Oz is a name.
No. You're repeating what you said before. I would like you to repeat what you just said. You said something that I'm doing. Making a confusion. I didn't get what the confusion I'm making.
The confusion is that Oz name calls something a reference, which is not the same thing that the bean calls a reference, but because it has the same name, you are thinking that they are the same, but they aren't actually.
Yeah, no. So okay, so you're repeating, um, and then I'm gonna say the same thing again. Aside from this being a pointer, everything else fits, right?
Not really. You can't really like the only operations that are really specific to references in Oz are wait and wait to, which is a generalization, right? And is that basically. You can't really like willy-nilly generate a reference that points to nothing. It's not like a there's difference from a name because you can make a name, you can do a make ref in Erlang, and you don't really say what it refers to. It's just a thing.
Yeah, I think I got that. You're right. They are not the same thing using the same name. I agree with that because one is a point, one has a dereference operation and the other doesn't. However, what I am saying is that everything else aside from what I highlighted is the same. They are unforgeable. They can be local and they can be remote, and you cannot tell the difference.
Yes, in that respect, they are mostly the same.
And I agree that if you're being pedantic, names would be the proper alternative in comparison to Erlang references, because as you said, references in Erlang they don't point to something; they are a thing. They are identifiers, which are also unforgeable and they are constant. Names can be used for different kinds of identity and authentication abilities, blah blah blah. And then we have the ticket, which I never heard before, but apparently that's a thing. A ticket is a terminology of this chapter, is similar to a reference, except that it is valid anywhere, including outside a Mozart process. It is represented by an ASCII string. It is explicitly created in the reference and it is forgeable. Oh, so you can forge it. Um, so this sentence is kind of incomplete. It is similar to a reference, except that it is valid anywhere and it is forgeable. A computation can get a reference to an independent computation by getting a ticket from that computation. A ticket is communicated via a protocol or between the users of these processes. Usually these protocols can only pass simple data types, not arbitrary language references. But in almost all cases, they support passing information coded in ASCII form. If they do, they can pass a ticket. Reading this a second time because I read this earlier during the afternoon. This is just a worse reference, isn't it?
Kinda, but it has an ability that a normal reference does not have, which is it can live outside of Mozart.
But I don't understand what this means. Why can't you use a reference outside of Mozart for starters? What is
Because a
forbidding you of doing
reference,
that?
because a reference is basically a pointer to some object that exists in a running process, right?
Sure. What forbids you
How
from
can
using
you
that?
how can you take a reference, which is a pointer somewhere in memory, and put it on the wire uh, in a way that still preserves the same semantics of being unforgeable? You can't, right?
No. I'm not talking about the forgeability right now. I'm specifically just talking about valid anywhere, including a Mozart process.
No, including outside of a Mozart
Including
process.
outside a Mozart process, sorry. Why can't you just pass the pointer as an hexadecimal number and use everywhere else? What forbids you from doing
Because
that?
because then in the outside world that's just a number that doesn't really mean anything. And if you give a number to Mozart, it will be like, okay, this is a number. What do I do with it?
No, but what you said is also valid with an ask string. I can send you any string. It doesn't mean it's valid for me. It's if it's
No, no.
Oz code, it doesn't matter.
Uh,
Like it seems particularly arbitrary to say that a number is not a valid for
it
references, but an ASCII string is.
I mean, you could use a number, but then it wouldn't be the same number that represents the memory address, right? You would have to make like a monotonic counter probably would be ideal, because the idea of a ticket is basically, okay, I have this reference, I want to make this accessible outside of this current system, right? I want to put it on the wire, save it on a file, what have you, right?
Mhm. Mhm.
So what I'm gonna do is say, okay, I'm going to pin it to a global dictionary of the system. I'm going to say, okay, there is a number or an ASCII string or what have you that refers to this reference, right? And then outside of the system, I pass the number. And if you give me the number and say, oh, by the way, this number is actually referring to a ticket.
Exactly. So you can give the meaning to a number. You see? That's what I meant by saying, oh, if
No,
you have
no,
a
no, no,
pointer, just grab the number.
no, no, but you can't just use the pointer address because, first of all, addresses are not actually stable necessarily, okay?
That's
Because the
fair
garbage
enough.
collect because the garbage collector may be a moving garbage collector that compacts the heap. In which
Okay.
case, objects will be moving around, right?
Yeah, but that's still not a good enough reason to say that a reference is completely invalid anywhere, including outside of a Mozart process. Uh, I understand what you're saying. Is that it makes more sense and it is more convenient for it to be an ASCII string. That's fine. However, this doesn't seem to me like something that couldn't be pulled off using references. This property, the
No,
forgeability
it
is
is.
different.
No, it is
Okay, it is.
because you need to, like, a reference mean is a pointer to a live entity in an actual running system. What happens if you write the pointer to a file and then you shut down the system? That will become invalid, right?
I can do the same with a ticket, but yes.
You can do the same with a ticket, right?
Yeah.
Um, um, okay, that's not a good way to explain this. Okay, suppose I take the current address of an object and I put it on a file, okay?
Sure.
Then I run the garbage collector, and the garbage collector happens to compact the heap, which means that old address is no longer pointing to the same thing. It's no longer valid.
Yeah, if you have a compacting behavior of a garbage collector enabled, I understand, but I'm not trying to make it practical. I'm just trying to ask a question of this seems to me as something that could be pulled off by via a reference. You said it cannot be, and you were bringing
Because
to me a practicality issue, not a
it's not.
feasibility issue.
Uh, well, you were leaking. If you do that, you are basically leaking.
Oh, so
You're
it's a
basically
security matter.
no, no. You're basically leaking the fact that okay, I have this address, which is a valid object. First of all, you are leaking the fact that this is not gonna move at all. Because if you're using a compacting garbage collector, you can't use this strategy, right?
Yeah, no, I completely agree with what you said. If if it's because of a security thing that we don't want to leak things, I completely buy it. That's fine. I completely buy that. It's just because reading this a second time I was like, man, it would be a pain in the ass and there would be a bunch of issues, but why exactly I cannot just use a reference if I wanted to? You gave me a good reason. That would leak stuff. This won't. Okay, I buy that. And then URLs. A URL is a global reference to a file. Did you get what I said? Now? Is it okay?
Yes, it is okay.
Um, the file must be accessible via World Wide Web server. So a URL encode the host name of the machine that has a web server and a file name on the machine. URLs are used to exchange persistent information between processes. A common technique is to store a ticket in a file addressed by URL. Okay, and just for the record, why I was being a pain in the ass about this, Because I was trying to apply the Lisp mentality of having less things. If I don't need to create a new primitive with a new name, I won't. So I was trying to find a good reason to do that, and Marinho gave me a reason. Aside from the whole convenience, right? Because he wants to do the compacting with the garbage collection, right? So it's not only a convenience thing, but it's also a security thing. With distributed computation, all these four kinds of names can be passed between processes. References and names are pure names. They do not explicitly encode any information other than being unique. They can be used only inside a distributed computation. Tickets and URLs are impure names since they can explicitly encode the information needed to dereference them. They are ASCII strings and can be read as such. Since they are encoded in ASCII, they can be used both inside and outside a distributed computation. We're going to use tickets. And then there is the connection module, which essentially allows us to bind a ticket to a reference. The ticket can be taken just once if you use offer, and if you use offer unlimited, it creates a ticket for any reference X. This ticket can be taken any number of times. And then you have the take, creates a reference X when given a valid ticket in T. When the X refers to exactly the same language entity as the original reference that was offered when the ticket was created. A ticket can be taken at any process. If taken at a different process than where the ticket was offered, then network communication is initiated between the two processes. So this is the bridge. So this is what the application programmer will have to be doing in order to specifically add distributed capabilities. So here's an example of the record. So you create this record and you use the offer unlimited X and stuff like that. Creates a ticket and displays it in the merged emulator. Any other process, blah blah blah. Here's is what the other process does. Right? So you grab the ticket, and then the question becomes how I'm gonna send the ticket because this is another process. We're gonna go there. To make this work, we have to replace tickets comes here by what was displayed by the first process. This is kind of obvious, but well. The operation connection.take takes a ticket and returns a language reference, which we put in X2. So a reference is essentially working, as Marinho said, as a data flow variable.
Yep.
Which then begs the question why we're using a different name for it. Well, c'est la vie.
Because if you're using a different language that doesn't have like unbound variables, everything is bound, right? Then it's not really a data flow variable. It's just a reference.
That's fair enough, but then it's missing a footnote saying that in NOS a reference is a data flow variable. But man, I'm being a bit too pedantic today. Where were we? Here, sharing functions. Okay, see, though, this is where it starts to get cool, right? So this is where the power it starts to be explicit. You have a full function, and you're just creating a ticket for it, and somebody else can call your function. You can do that in
Very
Erlang.
nice. You can do it in Erlang, yes.
That's cool. And then sharing the reference itself, so you have that, and then you can take it, and this will block until X is bound. So that's cool. Ticket distribution. So then we have local distribution. This uses the local file system. The destination process has to be connected to the same file system as the source process. This works well on LAN. And we have global distribution, URLs. We're gonna now talk about the pickle module. Is that how you pronounce that, pickle?
It is, yep. It's a pickle.
We recall that the pickle module has two operations, save and load.
You can turn yourself into one as well.
Yeah, so why does this matter? Because remember that in here I said that how you're gonna know the ticket. This is how you're gonna know. Because how you're gonna in here we can just copy paste from the result of this and paste it in down here. But that doesn't happen if you're in different computers. So how do you do that? This is how you do that. Ticket distribution, in particular the save and the load. So you're gonna save that stuff into an URL or into a file in a file system. And then it works like this. And then to load it works like this. So pretty simple. The main limitation of pickles is that the only values can be saved. One way to get around this is to make a snapshot of a state of information, like we mentioned before. Make a stateless data structure that contains the instantaneous states of all relevant stateful entities. This is more complex and pickling since the stateful entities must be locked and unlocked. If situations have a deadlock must be avoided. So this is a whole set of new problems if you needed to do stateful stuff.
Yeah, just don't use state for this. That's just easier.
Um,
Or use tickets, but then you're limited to a running process, as the next paragraph explains.
and if you're gonna do this type of shit, use transactions.
Yeah.
We don't need such a complete solution in this case. There is a simple technique for getting around this limitation that works for any language entity. The idea is to store a ticket in a pickle. That's required, right, in order for the other stuff to work. This works. Tickets are strings, yeah, which are values. This is a useful technique for making any language entity accessible worldwide. So then we have offer and take operations that use the connection module in conjunction with the pickle module. This is just helpers to make a little bit easier typing. And then we have stream communication from chapter 4. So this is the consumer of data, this is the producer of data, and we are using the take, we are using the offer. Things like that. Things like that. This sends the stream across the network from the producer process to the consumer process. This is efficient since the stream elements are sent asynchronously across the network. Because of the thread scheduling, the stream is created in batches, and each batch is sent across the network in one message. We can do the same with lazy streams. Then we have a port, which is a FIFO channel with an asynchronous send operation. Asynchronous means that the send operation completes immediately without waiting for the network. So this is how that's going to look like. You create a port, you do an offer, and then on the other computer you do the take with the tickle file, and you can continue using the same port from before. And remember, the take and the offer are just helpers for you to load something and immediately take it, or do the offer unlimited and immediately save it. That's why these things are there. That's what they do, and that's why this is why this is so convenient. And then we have distribution of state. So simple state sharing using a simple cell. Very okay, nothing too crazy about it. And now it goes to distributed locking. So figure 1, yeah, 11.4. So this is the same aside from reentrants.
Yeah, this is the version that we saw before they went into detail about how to make it reentrant. It's kind of cool that the same function works in a distributed setting. It's very nice.
Yeah, that's very cool. If multiple threads attempt to access the block body, then only one is given access and all the others are queued. The queue is a sequence of dataflow variables. Each thread suspends on one variable in the sequence. It will bind the next variable after it has executed the lock body. Each thread desiring a lock therefore references two variables, one to wait for the lock and one to pass. We've seen this before as well. One to lock to the next thread. Each variable is referenced by two threads. Yeah, this is essentially the deadlocking avoidance thing that we've seen before.
Yep. Yep.
Sharing objects and other data types. So now we're gonna do a full object, so you have the coder there. But the important thing is that any process that takes the object's ticket will reference it. The Mozart system guarantees that the object will behave exactly like a centralized object. For example, if the object raises an exception will be raised in the thread calling the object. So this is very important because this is kind of stationary at this moment, right? The object.
Well, it's just using new, so technically it isn't actually.
But it's behaving like one. Because it's
Well,
saying that
well,
the system will guarantee that the object will behave exactly like a centralized object.
yeah, centralized, not stationary.
Okay, what is the difference between those two words in this sense?
Difference is whether you're using distribution or not.
But you are. This is
But
why
it
we are
behaves like it.
doing the
Yeah,
offer.
but the point is, yeah, but the point is that it will behave as if it wasn't distributed. You see?
It will behave like it wasn't, but it is. That's my
Yes, but
question. It is. So
it is
then,
distributed, but the semantics are the same. That's the point.
well, but with a stationary is also the semantics are the same, no?
Well, yes. The only difference between them is actually like if you're using a mobile state or a stationary state, the only difference is the distribution behavior, but the semantics are still the same. Yeah.
Yeah, no, but then my confusion is how is this different than being stationary in this case? Because you said it yourself. It is distributed, but it behaves the same semantics. Both sentences are also true for stationary, isn't it?
It is. The point is that by default, well, we'll see this in a bit, but basically by default, mutable things that are not ports, they use that caching behavior. So yeah, this example is not technically stationary because it's not explicitly asking for it to be stationary, so it uses the default, which is mobile.
Oh, but in that case, I think I'm confused because if they are using the mobile, they are doing the copy, right?
Mm, they are using the copy, kinda. The thing is, we're gonna see this a bit later, but basically only one node in the distributed system can write to a particular mutable thing at the time, you see?
Sure, but then I still don't understand this because if they are doing the copy, this is not
No,
exactly
no,
like
no,
a
no, no.
serialized object. So they are
No,
not
no,
doing
it's
the
not a
copy.
no, no, a caching is not a copy actually. It is well, actually
I
there's
think
a
we need to
difference
go back because I
between
think it uses the verb copy. So let's go back. I'm getting more confused. Wait a moment. Is it in here? Where is it?
it's on the I think it's the last paragraph in this page, no?
Oh, here. Depending on the application's needs, entities may be given different distributed behaviors. For example, no, it's not in here. It's where it explicitly mentions the caching with italic. This is in quotes. Where is the italic stuff?
I think it's the first bullet point on the next page, no?
Here, first bullet.
Oh wait, no,
Um,
this doesn't talk about caching.
yeah, the copy is here, but this is for stateless, so this is not what I want to ask. Yeah, so maybe it is this one. So for example, mobile object, also known as cache objects, move to the process. Yeah, move to the process that is using them. What does that mean if it's not a copy? Then I understood it wrong. This is not a copy. But then what does it mean to say move to the process that is using them?
Basically, you need to send a message. This gets explained later when we get into the actual distribution protocols. But basically, each cell, each mutable cell has a home process, right? And if
Hmm.
you want to write to the cell, you have to send a message to the home process saying, "Hey, give me the cell. I want to write to it." And then the process needs to say, "Okay, here's the cell. I'm transferring ownership to you. It now belongs to your process."
Ah, so the
Which means
move
that,
is a like an ownership move.
yeah,
Ah, got it. Okay, so yeah, this actually makes sense because if it was a copy, then you'd have to synchronize the copies, right? That's a lot more overhead. Yeah.
yeah, it's not really a full copy. Like you have
No, it's not a
you have
copy at all.
it's not a copy at all. You have a cached copy of the state if you have a reference to it that you don't own. But then if the owner of the cell writes to it, it will send you a message saying, "Hey, I just wrote this thing. The current state that you have is now invalid. So
No, no, no.
here's."
Do you have the ownership, so it's like a dataflow variable to manipulate it yourself, or do you have a copy? Now you're getting me confused, my man. Because
No,
you
you
just
have a
said that if you have an outdated version, the home process will tell you have an outdated version.
actually
Why
that's
would
not
you
quite
do that?
correct.
Okay,
Well,
go.
actually that's not quite correct. What actually happens is you have a reference to the mutable cell, right?
Sure,
And then you have the operations on the cell. If you try to write, you need to take ownership if it's not yours already, right?
sure.
If you try to read, then you send a message to the owner saying, "Hey, what's the current state?" Um, and then he'll reply you the current state, right? And you're going to cache that so you can try to avoid a round trip every time you have to refer to the same thing. But that means this implies actually that when the owner writes to the cell, it needs to send you a message saying, "Hey, I wrote to the cell. Your cached value is invalid because I wrote."
Okay, so let me see if I understand. If you write it, if you want to write it, you have to ask ownership to the owner, the current owner of that. And how do you do the writing? Do you write yourself or do you ask the owner to write it?
You take ownership first, and then when you get the ownership, the cell is now local to you, so you can just write it yourself.
Okay, and then to read, then you do the copy.
Yes, and the copy
Ah.
is just to avoid repeated network trips. Um, but then that means if the owner writes to the cell, it needs to invalidate all the cached copies so they don't read stale
Am
data.
I crazy? Because I don't remember reading that here.
It's not here. It's actually in the section that we're gonna do next session.
Okay, but then this is bad because then this is very vague.
Well, this is an introduction chapter, so
Exactly. It's a misleading introduction chapter. It's
well,
bad.
it says that it moves. It doesn't say copy.
No, exactly. But it's not doing this differentiation thing that you just did. You don't see the difference that what you said is like two extra lines in here, and they didn't do it, and it's just up in the air, whatever it means. Because now that I think about it, this cached has it's meaningless without the context that you're just doing that for reading. So bad, bad. Yeah, and then if you do if you want to write, but you're not writing yourself, like taking the ownership and doing yourself because it now becomes local to you, then it's stationary because then you're calling the guy that owns and ask him, right?
Yeah, yeah.
Okay, now yeah, that actually is written here. Got it. Okay, sorry for that. Sorry for the tangent there. So let's go back to where we were. I think we were here. Yeah, distribution of state. Cool, cool, cool. Yeah, we are talking about the locking, right? And then we already talked about that. Then we have the object, and then we are talking about the Mozart system guarantees that the object will behave exactly like a centralized object. So which one is this one? Is this the one of the cached one, or is this the one of the stationary one?
Um, this is using new, which means it's just using the default behavior, which means this is the cached one.
Okay, so this means that you ask ownership. If you want to read, you're gonna just do a caching, and if you want to write, you're gonna do it yourself because as it is written here, it becomes local to you.
Yeah.
Cool. Distributed lexicoscope. Yeah, this is also very cool. This is very cool. And we also have to tackle this in our stuff. So distributed lexicoscoping, a procedure that references a language entity. We continue to reference that entity. Whatever. What does that mean? Look at this code. So you have a C, which is a mutable cell. You have an increment function that reads, does a plus of the argument with the current value of the C cell, and you are doing an offer twice, so you're like, how should I say? This is making it distributed, essentially.
Yeah, yeah, you're making two tickets, one for the cell and one for the function that references the cell.
So other people can now take those tickets and do stuff with it.
Yep.
Inc will always reference C, no matter from which process it is called. A third process can take C's ticket and change the content. This will change the behavior of increment. The following scenario can happen. Process 1 defines C and inc. Process 2 gets a reference to inc and calls it. And then process 3 gets a reference to C and change its content. When process 2 calls inc again, it will the new content of C. Semantically, this behavior is nothing special. It is a consequence of using procedure values with network transparency. But it sounds complicated as shit, isn't it? Because you have to update the tickets as the people are changing parts of it. So as they are doing their stuff, you need to like synchronize and do all that stuff. Otherwise, the lexoscoping property will get nuked.
Yeah, there's a lot of stuff going on in the background to make this happen.
Yeah. Distributed lexoscoping is important for sanity reasons. I wouldn't even say
Yeah.
for software engineering. Entities that are moved or copied between processes will continue to behave according to their specification, and they won't get nuked because it's distributed. The importance of distributed lexoscoping was recognized by this person in a simple functional language with object-based extensions that was designed for experimenting with network transparent distribution. Okay, now network awareness. So this is actually, I'm like the elephant in the room. The elephant in the room. Uh, we should be clear how network transparency works because up until now we were kind of like taking for granted. The distribution pre-implementation of Mozart does many different things. It uses a wide variety of distributed algorithms to provide the illusion of network transparency. At this point, you may be getting uneasy about all this activity going on behind the scenes. So what are the questions that actually matter? What network operations does the system do to implement transparency? And are the network operations simple and predictable? Is it possible to build applications that communicate in predictable ways? Um, well, the answer to the second question is kind of obvious because if you implement network transparency, this means that you can already leverage the declarativeness of OS. So this is already a yes, assuming you did it. As we will see, the network operations are both few and predictable, in most cases exactly what we will be achieving by explicit message passing. Yeah. This property of the distribution subsystem is called network awareness. Yes, Mari.
I was not gonna say anything actually.
We now give a quick summary. So, a quick summary of what? Of the network operations done by the most used language entities. The basic idea is the following. Stateless entities are copied, binding of data flows are multicast, and ports are stationary with FIFO sense, and other stateful entities use a consistency protocol. So numbers, records, and liters are stateless entities with structural equality. Separate created copies cannot be distinguished. The values are copied immediately whenever a source process sends a message to a target process. This takes one network hop. Many copies can exist on a target process, one for each message sent by the source process. Procedures, functions, classes, and functors are stateless entities with token equality. That is, each entity, when created, comes with a globally unique name. The default protocols needs one message, possibly followed by one additional round trip. In the first message, the name is sent, if the name already exists in the target process and the value is already present and the protocol is finished. Well, that's really not true, because maybe the thing changed, right?
Actually, no, because if the thing changed, that implies that there's an embedded reference to something that's stateful, and the reference will be the same.
Not necessarily. I can
Well,
send
yes,
you a
it will be.
function that is stateless, but I can send you an updated version of the function with the same name.
That's a different function with a different name, actually.
No, but I'm sending the same.
No, 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 no. For it to be the same, that means that This is name not in the sense of the name given to a
Ah,
variable that holds. It's actually a
yeah,
name in the
the
name in
name
the
of
distribute.
yeah.
Yeah, in that sense.
Okay, so then my bad. Then yes, right? Because then a function would have a different name with capital N, even though it's the same name in the code. Uh, if not, then the value is immediately requested with a round trip. This means that at most one copy of these entities can exist on each process. Data for variables. One message is sent to the process coordinated the variable protocol. This process then multicasts one message to each process that references the variable. Same thing as the runtime probably. Object
Yeah.
serves and locks, so they are distributed state. Mobile cached objects, stationary objects, and asynchronous objects. Each protocol gives good network behavior for a particular pattern of use. The code example we gave before defines a mobile cached object. A mobile cached object is moved to each process that uses it. Yeah, is moved. This requires a maximum of 3 messages for each object move. Once the object has moved to a process, no further messages are needed for invocations in that process. Later on, we will redo the coder using stationary and asynchronous. And streams and ports. So a stream is the same as as the runtime with threads. And then ports, because they will make them stationary by default, they will also inherit the same semantics as the runtime.
Yep.
Aside from the RMI, apparently. It is clear that the distributed behavior of these entities is both simple and well defined. Cool. So common distributed programming patterns. That's the last one for today. Stationary and mobile objects. So in the coder example, the object is mobile. This gives good performance when the object is shared between processes. The object behaves like a cache. On the other hand, well, behaves like a cache when reading. It's important.
Yeah.
That's why I was so confused. That's why I was saying copy. On the other hand, it is often useful to have an object that does not move, a stationary object. For example, the object might depend upon some external resources that are localized to a particular process. We're gonna get around this limitation later, but for now, let's say that that's the case. We're gonna make it stationary because of the localized resources. Putting the object on that process can give orders of magnitudes better performance, blah blah blah. And then we're gonna create another new instead of the default new. We're gonna use the new stat.
This is yeah. Note this was already introduced in chapter 7.
Yeah, new stat has already been defined, which essentially allows us to have a thread inside the new here. So then you actually just communicate via the thread that is running on the background. So that's cool. And we are abusing the lexoscoping to do that.
Yeah, basically we're exploiting the fact that ports are already stationary by default to force the objects to be behind a port so it never moves.
Yep, pretty much. Yeah, pretty much. Yeah, and then it looks the same, but it actually behaves differently. This creates a thread and a port situated on the home process. C is a reference to a one argument procedure. Now assume another process gets a reference to C, because you're gonna have to save the ticket somewhere so somebody can load it. Now this will transfer the procedure to the second process. That is, the second process now has a copy of the procedure C, which is it references by C2. Now let the second process call C2. Yeah, so you're essentially allowing like a backdoor so people can use it to make their stuff. In this case, you're just providing a procedure. This creates a dataflow variable A and then calls C2 locally. This does a port send. The references to A and X are transferred to the first process. At the home process, object A is executed. Okay, so this is actually the nitty gritty difference, right? So the
Yeah,
stationary, you are actually doing callbacks, and in the cached mobile version, you are actually it becomes local to you actually. So that's the main difference.
indeed.
At the home process executed, where object is the actual coder object. If this exchange is successful, it's going to return normal, otherwise exception. Mm. you can also see that remote calls to stationary objects are more complex than calls to mobile cached objects. Obviously, because callbacks are always harder than doing it yourself.
Yeah.
Mobile objects are simpler because once the object arrives at the caller process, the subsequent execution will be local. How many network hops does it take to call a remote stationary object? Once the caller has a reference to the object, it takes 2 hops, one to send the tuple and one to send the results back. We can see the difference in performance between mobile and stationary. And then, as far as I can tell, try doing the both for both the mobile and stationary objects. How do you explain the difference? I haven't done this myself, but my understanding is that doing the stationary is going to be slower.
Yeah, because there's a bunch more of round trips over the network, right?
Yeah. Asynchronous objects in data flow. Um, how can we make this asynchronous, right? So when you get on the network delays, you do asynchronous, because if you keep it synchronous, you're gonna have to wait. Well, you're gonna have to potentially gonna have to wait regardless if you are actually exchanging data flow variables and there is a blocking operation down there. But you are assuming that you can actually call it and the blocking procedure will happen all the way down later, so you can do stuff in the middle. First, do the send without waiting for the result, then wait for the result later when it's needed. This technique works very well with data flow variables. The result of the send is an unbound variable that is automatically bound as soon as its value is known. Because of data flow, the variable can be passed around, stored in the data structure. You can do all the crazy stuff that we've seen before. So then there is the code. That's how that works. And then you can just do the 3 gets here. If they are asynchronous, if the 3 dots here is actually a bunch of stuff, you can still be productive in doing the stuff, even though those 3 things are unbound. And then later, the final line of your thing, which is this one, it's going to block naturally because it's data flow.
Data flow is so nice.
I actually wonder how the experience may be of using them. Because one thing is to have admiration of something. The other thing is liking them because you use them. I never used them, so I don't have the second understanding.
I actually have some experience with them because promises and closure, the thing that closure calls a promise, is kind of like a data flow variable. The only difference is that it's not transparent. Like you have to explicitly dereference it.
Let me see. In the first scenario, the program does 3 synchronous calls and then it blocks waiting for them. On the second case, we do better by doing asynchronous. This calls slightly more. This takes more, slightly more than one round trip message delay before the calculation. And then the third one is the best of all, which is you know ahead of time that this is going to take some time, so you move those 3 lines up in your program, and then you keep doing things even though you don't need them yet, because you know it's going to take some time, and then you can finish faster because they already arrived at the time when you're actually going to use them.
Very
Uh,
nice.
yeah, yeah, that's very well. It's nice, but at the same time, I wonder if this could be done mechanically, in a sense. Like, wouldn't it be cool if the compiler could tell that, hey, I'm gonna move these 3 lines up because you don't need them aside from the final line, and but then how would the compiler know this is asynchronous, right? And all that stuff.
Well, the compiler would need to know
They actually
if
infer
this
a type
has
of this, right? So it could try to predict that, hey, this is asynchronous because you're doing a take here. So I'm actually gonna try to move this as soon as possible.
actually you would have to know if the C1 that you got is an active object or a normal object. Um, which I don't think you can check in NOS because that's actually encapsulated.
I don't follow your
So
logic. This is specifically for distributed programming. You know that.
no. Take is for distributed programming, yes. But what you get out of the take, you don't necessarily know what it is ahead of time.
I'm still confused. If take is already ahead of time known to be distributed, why can't you always just assume?
You know that the take will create a reference to some remote object, but you don't know ahead of time what that remote object is.
But it doesn't matter. That's my point. It suffices to know it's an object. Why does that info matter? That's what I don't
It
understand.
matters. It matters because you need to know in order to decide which how you're going to organize your calls. You need to know if the object is actually, first of all, asynchronous because it may not be, right?
Ah, okay, that's why you need to know. Because if this is a synchronous thing, you are screwed. Then you cannot rearrange this.
You can't. But then again, if it's synchronous, then you're going to use move semantics. So I don't know, trade-offs.
Sure. Yeah, but I understand now your point. You need to know what kind of object it is because if it's synchronous, you may be actually changing the behavior of the program. I was kind of like, oh, if it's asynchronous, and I can already use the environment to know if you're using them or not. I do have the freedom to rearrange them. But you're right. You cannot know ahead of time what you need to know at least a little bit of this object in order
Yeah,
to
it's
do
kind
this
of
kind of
tricky.
stuff.
It's kind of tricky, ain't it? It's transparent whether the object is local or remote, but whether it's synchronous or asynchronous is not actually transparent. It's something in the language semantics that we saw all the way back when we were talking about concurrency in chapters 5, 6, 7, you know.
Yeah. But in that case, would it be a bad idea to introduce an optional artifact the programmer could put here to help the compiler?
An optional artifact,
So for
like an
example,
annotation.
yeah. So for example, people in normal, like popular programming languages, usually have the keyword async for asynchronous stuff. Rather,
Ah,
whether this is real or synchronous or not, it doesn't really matter. And would it be a bad idea to keep like this is valid os, let's say in this hypothetical world, this is valid os, but you do know that these objects are asynchronous. Can't you like you may say, oh Lambs, but if you change that somewhere else in the code, you have to you have to go back here and remember to remove the asynchronous if you turn them synchronous then. And my answer to that is yes, but it's a double-edged sword, right? Because I am giving the ability to the compiler that I'm helping the compiler saying, hey, these three lines in line 300, 305, 6, 7, they are synchronous. Maybe the compiler put like in line 1, 2, 3 because of that.
uh, if you know that they are asynchronous and you, to the point where you can put an annotation in the code, then you have the necessary knowledge to judge if you should move it or not yourself, no?
Sometimes it's not that obvious, is it? Like maybe this is nested in a bunch of other code. Are you gonna have to like do that surgery yourself? But you're right. If you have the knowledge that this is asynchronous ahead of time, why did just you don't use the shortcut then? And that's a fair enough criticism. But well, I would like to imagine that well, scenario three is definitely the best one. Can we try to make that more frequent um, by doing it mechanically ourselves? That's what I wanted to wonder about. Okay, now we asynchronous objects with exceptions. So except yeah, that's nothing too crazy. Separating timing from functionality. Uh, a distributed model completely separates timing issue from programming techniques because we have seen that the program code can be executed in synchronous objects and asynchronous, and it is possible because of implicit synchronization with data flow variables. Of course. Then we have a compute server. Ah man, it's already 1 hour and 20 minutes. So we have the compute server, and then we do new stats to make it stationary, and then you have the Fibonacci example. So this one is doing it remotely, and this is doing it locally, right?
Yeah.
And then there are two problems that we want to be able to solve. Access to remote resources, because what if I want to run, from the perspective of the client, a printer from the server? Then there's a problem, because I don't have the scoping necessary in the client to use the printer.
Yeah.
Well, functors time. So we're going to actually exploit the fact that, first of all, functors are first class. And second of all, we can actually have access, due to the imports, to other modules that the server will have access to. Um, and then the server will actually do the module.apply, which is going to load the function, including installing things. This is very cursed from a reproducibility perspective, because you are, in fact, mutating the environment of the server. So that's pretty risky.
Are you?
Yeah, it's literally saying
Oh,
it.
oh, it installs them, yes, but um, you're not using the return value, which returns a list of modules, right? You're not binding them to anything.
Yeah, but installing it is already dangerous enough, don't you think? Like, what do you mean? What do you mean?
I mean, this is a not functor, so its behavior is constrained by the semantics of the language.
Yeah, and I can change. Um, I can install things. Like, I don't know. To me, this is pretty self self reporting as dangerous, because anything that is changing the environment where the program is running should be taken very seriously and carefully, and it's very delicate, it's very sensitive. You can do very bad things doing that. And then you can actually do then the new syntax becomes like this, and then the other thing also applies, right? So the server can actually use things from the client, right? Because I think there was two things, right? There were two open ends. This the client wanting to use server things, and the server wanting to use client things, I think. But you can pull that off using functors for both.
If the server wants to use client things, the clients can just send the things that the server wants to use.
Sure, sure. Um, yeah, yeah. Kind of what we're gonna do next, right? With the dynamically upgradable compute server. So this allows
Yeah.
us to not have downtime to upgrade the server, and we're gonna do this by returning a procedure which is called upgrade. And we can actually do stuff with that, and we can also override things on the fly. So this is the new run of the server, and we are using the new upgradable stat, which is this procedure that allows you to actually return this procedure here, which is doing the overriding at runtime. All of this at runtime. And then the compute server can be upgraded as many times as desired, since garbage collection will remove. Yeah, we are exploiting the garbage collection. It would be nice if the client could find out how many active competitions there are on the compute server before deciding what not to do. Yeah, you can do anything. You have a funky lambda. You can do anything. Um, and then close distribution. So is when an application completely manages distribution structure. For example, a server application that runs on a cluster can itself create all the processes that will run the cluster machines. This is essentially saying that you can do OS for DevOps.
Basically.
Instead of having to use whatever, you can just use this and have your. It's a kind of the same philosophy of Erlang, that instead you have your tree of processes being done on the language level instead of being done via any other external tool. usually associated with DevOps development. This is the same kind of principle, but going to the moon, because this allows you to go even further than that. We just seen an example, right? Although in Erlang, I also think you can do such a thing, such as upgrading on the fly.
You can, because in Erlang, modules are dynamically linked, and you can say, okay, being node, here's the new version of this module, load it.
Yeah. Uh, so here's an example. This creates a remote process and a local object R, which is a remote process manager. If no arguments are given, then the remote process is created on the same machine as the caller process. With the right arguments, it is possible to create processes on other machines. So you can literally just do something like that. Creates a remote process on this URL. By default, the remote process will be created using a remote shell. In order for this to work, the host must have been set up properly beforehand. The remote process can also be created with SSH. And you can also use the functor trick as before. Calling the manager with this installs functor f on the remote process and returns the module in X. There is a master-slave relationship, but it's kind of obvious and natural. The original process can change the new process priority, put it to sleep, and even terminate it as if it is necessary. Again, same philosophy as the Erlang thing. You can restart them, you can reboot them, change the configuration on the fly, and you can do whatever you want with them.
What language is this in?
Oh, hello, Ace. This is Oz.
This is OS.
Oh, Oz. Okay, okay.
Yeah,
I've
so
heard of it, but I've never looked into it.
It's
yeah,
a really good
it's
language.
yeah, it's
Yeah, I've heard good things.
it can do many crazy things. My only hiccup is that it is dynamic, but it's very educational. It's multi-paradigm to the moon. Like it puts, I think it's fair to say that it puts Common Lisp to blame, like shame.
Yeah, isn't Oz related to like I think it was either inspired by or inspired languages like Self, I think, right?
I had never heard of that.
Uh, Self. I'm not sure if self. Maybe, but I don't know.
Yeah, but
Yeah, I
you,
don't really know the relationship between Oz and self, to be honest. I know self, the
Oh no,
research that
never
went into
mind.
that eventually found its way to Java, but I don't know
Yeah, never
about.
mind. No, I think it is unrelated. Yeah,
yeah,
because it's influenced by Erlang, Lisp, and Prolog, and then it influenced Alice and Scala.
yeah. So, but anyway, a language that puts the multi-paradigm of Common Lisp to shame is like that's a big boss, big thing, because this like multi-paradigm and it's very well thought out to be integrated with all those paradigms in mind. Crazy. But let's finish the recording for now. So we're gonna finish the chapter 11 next time. So I'm gonna finish the recording now.